Hey everyone, welcome back to Abzyme Learning. Today we're diving into integration and differentiation. Let's get started. Before we jump into tips and tricks, let's ensure we understand the fundamentals. Think of it like building a house. You need a solid foundation before you can add the walls and roof. First, get familiar with the standard derivatives and integrals. These are your building blocks. Memorize them like you would your multiplication tables. Start with the most common ones and gradually build your repertoire. Next, make sure you're comfortable with the fundamental formulas like the back of your hand. The key here is practice. Now that we've covered the basics, let's talk about how to approach a differentiation or integration problem. The first step is like a detective's work. You need to identify what kind of problem you're dealing with. For differentiation, pay close attention to the wording. Are there keywords like rate, slope, or instantaneous change? These are your clues. For integration, look for clues that tell you whether it's a definite, indefinite, or improper integral. Identifying the problem type is crucial because it sets you on the right path. Once you've identified the problem type, you can then select the appropriate formulas and techniques to solve it. Take a moment to analyze the problem before you jump into solving it. Now that we've identified the problem type, our next step is to simplify the expression as much as possible. This is where a little bit of algebraic manipulation can go a long way. Start by looking for opportunities to factorize or expand expressions. Simplify complex fractions by finding common denominators or using techniques like multiplying by the conjugate. Don't forget about trigonometric identities. Sometimes rewriting trigonometric functions using identities can significantly simplify the expression. Simplifying expressions may seem tedious, but it will make the rest of the problem much more manageable. Break down the problem into smaller, more digestible pieces before applying calculus. Let's talk about one of the most powerful tools in your calculus arsenal, the chain rule. This rule is essential for differentiating composite functions, which are functions nested within other functions. Understanding the chain rule can significantly simplify your calculus problems and save you a lot of time. This rule is your best friend when dealing with composite functions. It allows you to break down complex problems into more manageable parts, making it easier to find the derivative. The chain rule states that if you have a function y equals f of g of x, then its derivative is given by dx equals f prime of g of x times g prime of x. This might sound complicated, but it's just a matter of applying the rule step by step. Think of it like peeling an onion. Each layer represents a different function, and you need to peel back each layer to get to the core. You start with the outermost layer, the outer function, then work your way inward. By understanding each layer, you can simplify the problem and find the derivative more easily. The chain rule might seem intimidating at first, but with practice, it becomes second nature. The more you practice, the more intuitive it will become. One of the best ways to get comfortable with the chain rule is to practice it with different types of functions. Try applying it to polynomial functions, trigonometric functions, and even exponential functions. Remember, the key to mastering the chain rule is to break down the problem step by step and apply the formula systematically. With consistent practice and a clear understanding of each function layer, you'll find that the chain rule becomes a powerful tool in your calculus toolkit. Now let's tackle two more essential rules for differentiation, the product rule and the quotient rule. The product rule states that the derivative of the product of two functions, u and v, is given by uv equals u plus uv. The quotient rule tells us how to differentiate a fraction where the numerator and denominator are both functions. The rule states that uv equals u minus uv over v squared. A helpful mnemonic to remember the quotient rule is low d high minus high d low over low squared. Just like with the chain rule, practice is key to mastering the product and quotient rules. Work through a variety of examples and don't be afraid to make mistakes. These rules are tools to help you differentiate complex expressions. Sometimes we encounter functions that involve products of multiple functions raised to various powers. Differentiating these expressions using the product rule can become quite messy. That's where logarithmic differentiation comes to the rescue. The key idea is to take the natural logarithm of both sides of the equation before differentiating. This step transforms the product into a sum. making it easier to differentiate. Logarithmic differentiation is particularly useful when dealing with functions that involve products, quotients, and exponents. It simplifies the differentiation process and makes it less error-prone. Now let's shift our focus to two special types of functions that appear frequently in calculus, exponential, and logarithmic functions. These functions are not just abstract mathematical concepts, they have real-world applications that make them incredibly valuable in various fields. For exponential functions of the form y equals e to the kx, the derivative is given by d over dx of e to the kx equals ka times e to the kx. This means that the rate of change of the function is proportional to the function itself, a property that is unique and powerful. This property makes exponential functions essential in modeling growth and decay processes. Whether it's the growth of a population, the decay of a radioactive substance, or the increase in an investment, exponential functions provide a precise mathematical framework. Logarithmic functions, on the other hand, are the inverse of exponential functions. This inverse relationship is crucial because it allows us to solve equations involving exponential growth or decay by transforming them into simpler logarithmic equations. The derivative of the natural logarithmic function, y equals ln x, is given by d over dx of ln x equals 1 over x. This derivative is fundamental in calculus because it helps in solving integrals and differential equations. Understanding the derivatives of exponential and logarithmic functions is crucial for solving a wide range of problems in calculus and beyond. These derivatives are tools that enable us to analyze and interpret various phenomena. These functions appear in fields like finance, biology, physics, and engineering. Their applications are vast and varied, making them indispensable in both academic research and practical problem solving. Sometimes, we encounter integrals that seem overwhelming at first glance. The good news is that we can often simplify the integration process by breaking down a complex function into smaller, more manageable parts. This technique, known as splitting the function, involves dividing the integral into a sum of simpler integrals. For example, if you have the integral of x squared plus 3x plus 5, you can split it into 3 separate integrals. Each of these individual integrals is much easier to solve than the original integral. By breaking down a complex integral into smaller, more manageable pieces, you can make the problem much less daunting. The substitution method is a powerful technique in integration that allows us to simplify integrals by making a clever substitution. This method is a cornerstone in calculus, often introduced in introductory courses, but used extensively in more advanced studies. This method is particularly useful when we encounter integrals that involve a composite function and its derivative. By recognizing these patterns, we can transform a seemingly complicated problem into a more manageable one. The key idea behind substitution is to replace a complex expression with a simpler variable, making the integral easier to solve. This approach not only simplifies the computation but also provides deeper insights into the structure of the problem. For example, if you have an integral of the form f of g of x times g prime of x, you can make the substitution u equals g of x. This substitution transforms the integral into a form that is often much simpler to integrate. This substitution often transforms the integral into a simpler form that can be easily integrated. Once the integral is simplified, the process of integration becomes straightforward. After integrating, you can then substitute back the original expression for u to obtain the final answer. This final step ensures that the solution is expressed in terms of the original variable. The key to mastering the substitution method is to practice identifying suitable substitutions and applying the technique systematically. With consistent practice, this method becomes an invaluable tool in solving complex integrals efficiently. Integration by parts is a powerful technique that allows us to integrate the product of two functions. The formula for integration by parts is the integral of u dv equals uv minus the integral of v du. To apply this formula effectively, you need to choose u and dv wisely. A helpful mnemonic for choosing u is LEAT, which stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. Once you've chosen u, dv is simply the rest of the integrand. Integration by parts might seem intimidating at first, but with practice it becomes a valuable tool for solving a wide range of integrals. Remember, the key to mastering integration by parts is to choose u and dv strategically, apply the formula correctly, and practice.